Hello, my name is Islam Shahata and I am a PhD student and a teaching assistant with Department of Engineering, Mathematics and Physics, Faculty of Engineering, Alexandria University. I am the corresponding author and the presenter of paper accepted at VTC 2024. This paper is a joint work with Professor Sharif Rabia and Dr. Ahmed Yahya from Alexandria University and Professor Ahmed Abdelmalik from Egypt Japan University. The paper title is Edge of Information Analysis for Task Offloading in an Energy Harvesting Status Update System. The outline of this presentation consists of: first, an introduction to the point of the research is presented, followed by the related work in literature. The proposed work model is presented, followed by the simulation results. Finally, the proposed work is concluded with some proposed points for future work. In recent years, real-time status update system is used in many applications, such as control forest fires and weather monitoring. In communication systems, two metrics are usually considered: throughput and delay. These metrics evaluate the network performance by measuring the average rate of successfully transmitted data and the required time for data transmission respectively. However, the data freshness, which is related to the generation time compared to the current time, isn't reflected in these metrics. Consequently, a new metric called Edge of Information is introduced to measure the data freshness. Edge of Information is the elapsed time from the instant of update generation to the latest delivery. Most commonly used approaches for analyzing the edge of information are sample bus analysis and stochastic hybrid system. Some applications need processing the sensed data before transmitting it as a status update to the destination. For example, in autonomous driving, the status packet may be an image, and the processing is needed to extract the information before delivering it to the controller unit. These systems are usually called computation-intensive status update systems. There are two issues in the local devices: the low processor capability and the limited energy. The first issue can be dealt with offloading the data to be processed at the mobile edge computing server. The data can be offloaded totally, where all data is offloaded to the MEC server, or binary offloaded, where the data can be processed at the local server or totally offloaded to the MEC server. Finally, the data can be partitioned, where a part of the data is processed at the local server and the other part is offloaded to the MEC server. The second issue can be dealt with energy harvesting technology. This table shows that a few numbers of papers analyze the edge of information in computation-intensive status update systems. These papers consider the binary offloading case and derived a closed-form expression of the average edge of information. However, these papers extended the previous work by assuming the partial offloading case. Unlike the previous work, these works derive the moment-generating function of the edge of information, but they consider the totally offloading case. This paper extended the previous work by considering the energy harvesting technology. However, they determined only the average edge of information. Consequently, we propose extending this work by assuming the partial offloading case and deriving a closed-form expression of the moment-generating function of the edge of information. The proposed model consists of a source that generates a sequence of status update of some physical process. This data is processed using the local server only, or using the MEC server only, or using both together. The local server harvests energy from ambient sources according to a Poisson process with rate lambda h, and stores it in a finite battery with capacity B. The average processing time at the local server is calculated using this formula, where alpha is the offloading ratio to the MEC server, C is the required number of CPU cycles, D is the packet size, and FL is the average computing capacity of the local server. The average transmission time to the MEC server is calculated using this formula, where R is the average data rate of the channel. To facilitate the analysis, we assume that the required time for processing data at the local server and transmitting it to the MEC server is exponentially distributed with rate μL, which is given by this formula. Moreover, the MEC server processing time is also exponential with rate μE, where TE is the average processing time at the MEC server, which is given by this formula, where FE is the average computing capacity of the MEC server. We apply a zero-wait policy, where the packet is generated immediately once the local server becomes idle and has sufficient energy. We analyze the edge of information using the stochastic hybrid system in three different disciplines. In the preemption discipline, the old packet is replaced with new arriving one. However, in discarding discipline, the new packet is discarded. In the blocking discipline, the new packet is stored at the MEC server, and the local server is blocked until the MEC server finishes processing the old one. Now a brief overview of the stochastic hybrid system is presented. The stochastic hybrid system consists of two types of states, discrete state and continuous state. The discrete state is modeled using finite state Markov chain. Assuming the ergodicity of the Markov chain, the state probability vector converges to the unique stationary vector which satisfies this balance equation. After transition L occurs, the continuous state X is reset to X dash according to a binary reset map matrix AL. It's proved that the correlation vector between the discrete state and the exponential function e to the power sx of t converges and satisfying this equation, where lambda is the exponential rate of the transition and a hat L is the binary matrix whose elements are constructed using the reset map matrix. For preemption discipline, this figure shows that the set of transitions of the Markov chain. Applying the balance equation, we obtain the steady state probabilities. This table summarizes the possible transition and their associated parameter for the stochastic hybrid analysis. Applying this equation and using this table, we obtain the moment generating function of the edge of information for this discipline. Now we can use this moment generating function to obtain the average edge of information in partial offloading case and local processing only. For discarding discipline, its transition diagram and the steady state probabilities are the same as in the preemption discipline. Moreover, the set of transitions of this discipline is same as in preemption, except that the continuous state resulting upon the transition L equal 5 and 5k changes as shown in this table. We can find the moment generating function of the edge of information for this discipline for any given setting of battery size, using this equation and the set of transitions. However, it was hard to obtain the moment generating function for general setting of battery size. For blocking disciplines, this figure shows that the transition diagram, we can calculate the steady state probabilities for a specific setting. This table summarizes the possible transition and their associated parameters for the stochastic hybrid analysis. We obtain the moment generating function of the edge of information for this discipline in terms of steady state probabilities using these equations. Now, a numerical investigation of the proposed work is presented using the system parameters shown in this table. This figure shows that increasing the harvesting rate or the average computing capacity of the mix server decreases the average edge of information, because increasing the harvesting rate increases the available energy for data processing and transmitting. However, at high values of this rate, the edge of information decreases slightly because the battery reaches its maximum capacity and cannot store more energy. Increasing the average computing capacity of the mix server decreases the processing time of the mix server, which leads to decreasing the edge of information. Due to the assumption of the exponential service time, the preemption discipline gives a least edge of information. This is because the new arriving packet which carries new information has the same service time distribution as the preempted one. We can also notice that the discarding discipline gives the highest edge of information, because this discipline wastes energy in processing time in processing the discarded packet. Additionally, processing a new packet in the local server takes more time because the service time of the local server is greater than the service time of the mix server. Moreover, this figure shows that the simulation and analytical results are very close to each other. In this figure, it's shown that decreasing the average computing capacity of the local server or increasing the required number of CPU cycles increases the average edge of information because the local processing time increases. Moreover, this figure shows that the standard deviation increases by increasing the required number of CPU cycles, and hence at high values of this number, it's misleading to use the average edge of information only to expect the information freshness. This figure shows that in preemption discipline for all values of data size, or in blocking disciplines at low values of data size, increasing the offloading ratio decreases the average edge of information, because the assumed processing rate of the mix server is higher than the rate of the local server. However, in blocking discipline, when the data size is large and offloading ratio is high, increasing the offloading ratio increases the average edge of information. This is because the mix server will be busy for a long time, which leads to blocking the local server. From this figure, we notice that increasing the battery size decreases the edge of information. This is because the sensor can generate a new packet after finishing the old one without waiting for harvesting. Consequently, the proposed model gives a better performance in terms of edge of information compared to the model introduced in this work, which assumed total offloading and battery size equals 1. This figure also shows that the obtained result can be used to determine the minimum value of offloading ratios that satisfies some upper bound of the average edge of information. For example, in blocking discipline at B equal 2 and D equal 8, at least 65% of the packet should be offloaded to the mix server for achieving an average edge of information doesn't exceed 25 seconds. This work proposed a computation-intensive status update system with energy harvesting capability, where data can be processed at the local server or offloaded totally or partially to the mix server. In this work, the moment generating function of the average edge of information were analyzed for 3 disciplines: preemption, discarding, and blocking. The result shows that the preemption discipline gives the least edge of information and then the blocking one. Moreover, this work helps in selecting the offloading ratio, which ensures a maximum average edge of information. This work can be extended in the future by assuming the randomness time of generation packets such as Poisson arrival process. Moreover, for more realistic systems, this work can be modified by considering multiple sources and assuming a non-exponential service time. This paper is based upon work supported by Science Technology Innovation Funding Authority STDF Egypt under grant number 48186, and Professor Sharif Rabia is the project PI. For any question, you can contact me using the shown email. Thank you.